Hello, welcome everybody. This is JDK 9, the hidden gems. I'm Mikael Vidstedt. Until recently I used to be a JVM tech guy, and then I moved to the dark side and I'm now managing the JVM, but hopefully I'll stay technical enough for this to be interesting.
Hi, I'm Sandhya Viswanathan, senior software engineer and technical lead at Intel, and we work with Oracle and the OpenJDK community to optimize Java for Intel platforms.
Cool. So we'll be talking about hidden gems in JDK 9. This is the Oracle version of the slide that says that everything I'm about to say is a lie. I believe that Sandhya will have her corresponding slide at the end of the slide deck, so stay tuned for that. This being a presentation on JDK 9 at Java 1 shortly after we launched Java 9, clearly needs to mention Jigsaw. There's no way around that, right? So in theory, this could be a presentation on JDK, on Jigsaw specifically. So all the great stuff we've done to modularize the JDK, the cool tools we built to improve on that. So you can create your custom JREs. You can start out with this module graph that we have in the JDK. You can streamline that and only include the modules that you actually need for your Java application. I could talk about how you end up with runtimes that are very much smaller. I could also touch on support we've added to have multi-release jar files and in a way make sure that you can run your Java application no matter which JDK you're running on and seamlessly allow people to do that. And I could also touch on support we have added to Java C to make that even easier so that you can compile for a certain JDK release. These are all Jigsaw related things, so we're not going to talk about that. This is the hidden gems of JDK 9. We're going to try to touch on the other stuff that has gone into JDK 9. So all the small things that tend to sort of end up in the shadow, in the shade behind JDK 9 Jigsaw. I'm going to start on, by touching on tools and libraries quickly. I'm going to say something about Hotspot and JVM, and Sandhya is going to touch a lot on the performance improvements we've done. If you go to the JDK 9 page, you'll see something along the lines of what's on the right-hand side here. So we have some schedule and a bunch of features that we've added that we worked on. And it doesn't look much until you realize that the page is significantly longer than that. Thank you, Aurelio, by the way, for this slide and the animation. I don't have the management skill sets yet to create it myself. But if you want to go look at what's in JDK 9, you can do exactly this. You can go to the JDK 9 page and have a look. Hopefully, you'll get some inspiration from this presentation. When I counted the JEPs we have on this page, I ended up with something. JEPs are our JDK enhancement proposals. They're for relatively large features, either very visible or things that have very big impact, or large features. And in many cases, it's large features. So in JDK 9, we have 90 really big features. This is just counting the JEPs. On top of that, we have all the other improvements. So this is a big release for us. It contains a lot of different things. And again, we're going to touch on a few of them in this presentation. So starting with the tools and libraries. One thing we have added, and I don't think that's another thing, like no presentation at Java 1 here is complete without at least touching on JShell, because it's such a cool tool. Other runtimes have had support for REPL-based playing around with code for quite some time, and now the turn has come to Java. So JShell is a read, eval, print, loop tool that you can use to try out things, try out code, and experiment with things without having to create your Java class file and use Java C to compile it and deploy it and all of that. So I'm running JShell here. Hopefully you can see, well, maybe not the leftmost couple of pixels, but at least JShell. You can do obviously simple things like adding a couple of numbers. Why not assign a variable, and why not say, take that variable and add 4. These are all sort of standard simple things. You should recognize most of them. That's JShell in itself, but JShell also has other cool functionalities. So I'm going to actually demo another thing that we have added in JDK 9. The first thing I'm going to do is to say list.of, and then I'm going to tab. And JShell actually has support for printing out the Java docs for methods. It has tab completion and can also print out the Java docs. So you can get help in the JShell tool itself in case you're not sure what parameters the function takes. Method takes, I should say. In this case, it may be a bit mysterious when you look at this, but what I'm going to say next is that we've added a piece of functionality called convenience methods for collection. Convenience methods for collections, factory, whatever. A set of functions methods that make it easier to create collections with a smallish number of elements. So you can't use this to create collections with 100 elements, but you can use it for single element or up to 8 or so, 10 in this case, I guess. And the nice part about these things is obviously it takes less typing. What you normally have to do is to first create your list and then go add, and then you can start using the collection. With this, you can instead create a list of, let's say I'm going to add 3 elements to this list, and all of a sudden I have a list of 3 elements. What you can't see here, I guess I could force it, but the collection here is actually immutable. It's non-modifiable. So you get back something that is read-only. You can't actually add elements to it, you can't remove elements to it, and there are some nice parts to that that we can leverage inside of the JDK and the JVM to optimize the implementation of this collection. So if we, for example, find a better way of representing the data here in the background without the full-blown collection that we'd otherwise have to allocate to potentially support you adding an element later or removing an element later, we can optimize something that is targeted for exactly one element without any modifications to it. And that does can help a lot with footprint, but also with performance. As another example, I guess I could create some, we all love strings, so I'm going to create a hello world list here. And then just because I like streams from Java 8, I'm going to say for each system out println. And you'll have your string pieced up, or obviously what I also can do is put this together. Or collectors.joining. And you'll have your full hello world string. Another piece of functionality we added to streams while we're on the topic is a take while operator. So you can say, for example, that pick elements from this stream while this thing is true. Or while the thing isn't true, I guess. So I'm going to say while the component here doesn't equal comma, and I'm going to collect that again. And you'll only get the hello. There's also a drop while. So 2 new methods on streams. We like optimizing streams, and we've optimized streams a lot in JDK 9 as well. So improvements have gone in that general area. Speaking of concatenating strings, and I couldn't find a good way of showing this because it's very sort of low level and back-end-ish in nature. But one of the things we've done is to change the way we generate bytecode for concatenating strings, so for piecing strings together. In the past, so first of all, there's a lot of string manipulation in Java, so it's very important for us to get that right and optimize it correctly. And in the past, what we had was a series of concatenation, append operations that the JVM and the JIT compiler had to sort of try to pattern match and scrape out and piece together in order to make sense of the fact that in the end it's just concatenating 2 strings. What Java-C does, starting with 9, is to output a bytecode sequence that is much more obvious for us to work with. It's making use of the invoke dynamic instruction, which is an instruction we added very recently, the first and only instruction that has been added to Java. And it's using this instruction to make it easier for the JVM to detect this. The other nice part about it is that that same pattern, more of the implementation and the optimization opportunities are then moved into the libraries. So if in a future release of the JDK we find a better way of optimizing this, we have that same pattern, we can detect it, and again update the implementation of concatenating these strings in the background, and you will all get the benefits of that without having to change your code. So back to the presentation. I walked through JShell. I touched on convenience factory methods for collections. That was the order of the words I was looking for. And indify string concatenation, which is again the concatenation of strings. I have had backup slides in case the demo didn't work out. And if you want to know more about JShell, There are plenty of sessions during Java 1. I recommend that you go to at least one because JShell is extremely powerful. I have a slide at the end where if you forget about what was on that slide. Moving into the VM, one of the key things we've done on the JVM side is to switch the default garbage collector. It used to be the parallel garbage collector, but we have now switched over to use G1, our garbage first garbage collector, as the default. The G1 garbage collector has as its goal to provide both good throughput and low latency or low pause times. It is region-based, so the way this works in the background is that the whole heap is split up into the individual regions, and then it's the G1 collector chooses very carefully which regions it's going to try to evacuate, to empty and clean up so that it can later reuse that for new allocations. And basically the way it works is that it picks the ones that have the most garbage first, where the fewest objects are actually live still, and then it moves all those live objects out to somewhere else. And what you have after that is obviously a clean, empty region that you can start allocating in. So the name comes from the fact that it's taking the garbage first, as if, the regions with the most garbage first. The default pause time target for G1 is 200 milliseconds, but this can be tuned. So if you want more throughput, for example, and can tolerate more pause times, then you can tune it one way. Or if you want low pause times, but you can tolerate some throughput overhead, then you can tune it the other way. As I mentioned, G1 has been in the JDK for a while. It's been made default now, and we have made some improvements to the implementation of G1 to make it more performant. This is an ongoing effort, so as a matter of fact, if you would pick up JDK 10, take the code today and compile it, you would find that we have already improved on what's in 9. So there's a lot of activity going on here and a lot of improvements. But the end goal here is really to have a GC in the default GC be one that doesn't only care about throughput, but also takes low latency into account. And we believe that a lot of applications going forward will be in one way or another latency sensitive. It's not just bulk processing of data. If you want to know more about G1, there are at least a couple of sessions that will touch on that. So again, recommend you to go to those. On the topic of GCs, one of the other things we've done is to deprecate and remove some of the code we have in the JVM. Specifically, we have deprecated the concurrent mark and sweep collector, the CMS, or short, the CMS collector. CMS has traditionally been used in low latency use cases where you don't have very large heaps and where your application is relatively well behaved, if I put it that way. The challenge for us on the JVM side has been that the code base, the implementation of the collector has been very, very hard to maintain, and it has been very hard to evolve the other collectors while still making sure that CMS works the way it does. So what we've done now is to deprecate it. The goal is to remove this in a future release. We haven't decided which one yet. And the hope and goal here is to have the other collectors fill the void, if you so will. There will be cases where you may have to tune things differently, for example, and all that. So if you're using CMS, again, be aware of the fact that this is going away and that we very much appreciate feedback on G1 and the other collectors. Help us improve those. That's the future where we want to go. The other thing we've done, which I think affects fewer people, is actually remove some of the GC combinations that we had in earlier JDKs. This is something we deprecated in JDK 8 and that we have now removed completely in 9. There used to be something called ICMS, and there was also a set of different combinations of various GCs that seemed to be not very well used, let's say, and were again hard for us to maintain. So those are now gone. Other stuff we've done to improve things, both sharing, footprint, and performance, is work on something we call CDS. CDS is short for class data sharing. This functionality has been in the JDK for quite some time as well. It used to be limited to the Java base classes, the JRE classes themselves. But as of, I think, one of the 8 U updates, or 8 updates, I should say, or 9, we also now have support for application classes as well. So this is not limited to the GRE anymore. It's something that you can use for your application classes as well. And the way this effectively works is that you have a sort of training run where you run your application once, and what the VM will do is to read all the classes, format them, and put them in a way that the JVM likes internally, in a more optimized format for the JVM, and then store that into what we call the application class data, or CDS archive for short. It's effectively a shared library, much like you define on the operating system level. But it's not an ELF. It's not in the native format of the operating system right now, at least. And then that's your training run. And then for every subsequent run you do of the JVM after that, you can point it to this archive, and it will make use of the information that is in the archive and leverage that. One of the key things we've done in JDK 9 here is to improve on what goes into the archive. So it used to be that it was basically just the class data itself, the byte code and the side structures. But now we can also store interned strings. And this is also something that is evolving, so we're looking at adding even more to this going forward. You have 2 major types of improvements here. The first one is startup time. So since the VM no longer has to read the class data from your jar files or class files, and massage that and make sure that it's in the right format, and again, all of that, instead now it can just pick up this shared archive and it's already on the right format. You get startup time improvements. And in this specific case, we're looking at WebLogic Server, base domain, and we can see that the improvement is ballpark 25-30%, something like that. This will clearly vary a bit on your application, but I think we've seen that typically you'll see this ballpark number, 25-30% on startup time. So it's pretty significant. And the other aspect of this is footprint. So the fact that now more of the data can be shared across instances means that you have less waste, less footprint for the individual instances. And obviously the more instances you run, the better. This does assume to some extent that you're running similar applications, that it's either the same exact stack of software, or at least that they share some common frameworks and libraries. But I think from what we've seen, that's a very typical deployment environment, and I think it's even more common with environments like Docker, where you actually have the exact same image and you stamp out multiple different containers from that. So the nice part here is that this works together with Docker as well. As a matter of fact, if you place the shared archive in a layer that gets shared across Docker containers, then it will work very much like operating system shared libraries. And it may not look like we're saving a lot, so the bars here are the unique data per instance with and without AppCDS. It's the shared data with and without AppCDS, and it is the total footprint with and without AppCDS. And it may look like the bars are similar. You should note that the y-axis is logarithmic, but in the end, this actually does add up over time. So this is, in this case, 10 different instances. If you run even more, you'll get more sharing, and what we're seeing here is approximately 10%, which may not sound like a lot for like my laptop, but if you stamp that out across a data center with hundreds of thousands of instances, then it suddenly starts turning into real dollars. I want to mention that AppCDS will be open sourced. This is functionality that the CDS aspect has always been open, but the AppCDS aspect has been closed. But we're working on open sourcing this. I cannot promise which exact release it will go into, but suffice to say that we're very eager to get this out so as soon as possible. On a similar topic, we have AppCDS that takes care of Java class data. The other thing we worked on the last few years is functionality called AOT, or ahead of time compilation. So this is doing with AppCDS, with JIT compiled data, JIT compiled code, the same thing that AppCDS does with the class data. So you know, in a normal operating system shared library, you have the data aspect and you have the code aspect, and you package them as a lib something else probably. This is doing the same thing with code. So there's a tool called JOTC. You give it a class file and it will spit out a shared library. In this case, it actually is an ELF. You can't use it apart from in the VM, obviously, but it's still stored in that exact same format. So you basically do, again, sort of a training run, but in this case it's a tool that you run, and then for subsequent JVM runs, you point it to that shared library, and the shared library will be reused. The code itself is not as efficient and not as performant as what you would have with the online JIT, the server compiler we have inside of the VM. But the nice part here is that the code that is stored actually contains a lot of the information and profiling code that is needed to drive the optimizations later during runtime. And the server compiler will actually kick in and improve on this code on top of what's in the archive. So basically you get like the first sort of tier of performance using the AOT code, and then during runtime we'll optimize on top of that. The functionality is experimental in 9 and only currently available on Linux x64. That said, we're adding platform support over time, and similar types of benefits can be seen from AOT here. I have a slide on it. Actually, next slide is on that, so I'll wait with that. But you have startup, you have time to peak performance. Instead of having to go through the full cycle of first interpreting code and then compiling code with profiling, capturing code in it, and then optimizing the code fully in the end, we have already sort of shortcut the first part of that. So you have faster time or shorter time to peak performance, or reduced time to peak performance. And the code can obviously also be shared across instances, so you also get the footprint savings. In addition to being something that is useful to end users, this is also something we're planning on using internally in the JDK to be able to move our JIT compiler up into Java, to implement that in Java instead. Still work in progress, but this is functionality that is sort of a prerequisite for that. I won't go into exactly all the details of this slide, but I will say that it is showing basically that you have the default case, you have the case where you have only AOT, you have the case where you have CDS, and you have the case where you have both. And basically what it's highlighting is the fact that they're both improving things in themselves, but together is where we get the most benefit out of them. So together, CDS and AOT together is a very happy combination. If you want to know more about AOT, it turns out that we have at least 2 sessions on that as well. So again, I'll have a slide on this later at the end of the presentation in case you want to look at it. And I'll go through the rest of the slides really quickly. I'm sorry for that. Java Flight Recorder, I want to highlight that this tool has helped us internally find a lot of bottlenecks. This is functionality that captures information in a very fine-grained way, but in a very fast and efficient way. So basically, the goal is to have it default on and always collect all this data. And we also have some visualization help to show that. And again, we're using this internally to drive development. JFR is also being open sourced. Again, we want to try to do that as quickly as possible, but no quicker. And if you want to know more about Flight Recorder, or for that sake, Mission Control, which is the visualization tool, there are sessions on that as well. And I'll skip through these slides. I do want to say that we've unified our logging framework. We have a unified logging framework in the JVM now. There used to be like 4 or 10 or 20 or something, depending on which subsystem you had in the JVM. Now we have one, so you can control all the logging using this one framework, and I'm personally super happy to see that. This was a very fast snapshot of functionality. Here are other things that went into JDK 9 grouped together. And the whole week, obviously, you will have a chance to catch up on these different aspects. But hopefully that gave you a quick insight into the functionality aspect. And with that, I'm handing over to Sandhya for the performance part.
Thanks, Michael. So over the last couple of years, we have contributed to and collaborated on many optimizations in OpenJDK towards JDK 9. So some of the key optimizations include the vectorization enhancement, math, crypto, and compression acceleration, compact strings, and the new API support, and optimizing the new API for the Intel platforms. The Intel recently released Skylake platform in July, And unless otherwise stated, most of the performance runs are done on the top bin Skylake platform, that is the Intel Xeon Platinum 8180 at 2.5 gigahertz with turbo at 3.8 gigahertz with 384 GB of RAM. And we are comparing the latest JDK 8 release, the JDK 8 update 144, with the JDK 9, which is just released September 22nd. All the runs were done on the Linux platform. So on the vectorization enhancements, we extended the vectorization to 512 bits. The JVM JIT, as in JDK 8, already supports auto-vectorization. They do superword auto-vectorization. So that has been now extended to 512 bits to benefit from the AVX 512 that is supported on the Skylake platform. We do super unrolling of the vectorized main loop. There is reduction support is added. Vector loops with reduction in them are now vectorized. And also there is support for additional operations that get vectorized now. So I'll go into that details in the next couple of slides. So AVX 512 is introduced in the Intel Xeon Phi processor and is available on the Intel Skylake processor. It basically extends the SIMD to 512-bit wide. That means 64 byte operations can be done in a single instruction, or 32 short, 16 int or 16 single precision, and 8 double precision floating point operations can be done in a single instruction. There are 32 ZMM registers, which are 512-bit wide. So what we have done is to add support for code generation, AVX 512 code generation in the JVM JIT, and extended the SIMD vectorization. We've also optimized the array string intrinsic methods to benefit from AVX 512. So this is a small Java example that we have shown, that we have used to show the benefit between JDK 8 to JDK 9. The loop kernel does get auto-vectorized. Here there is the operation being done on elements of 2 arrays, and the result is stored in a third array. So this particular example with different data types and different operations is what we showed to show the benefit. So we are basically comparing the 32-byte vectorization that was available on the previous platforms to 64-byte, that is 512-bit vectorization that's now available in JDK 9. You need to use the use AVX equal to 3 JVM command line option to get the 512-bit vectorization. And we also show the benefit of alignment. JVM has an option called object alignment in bytes, which you can use to align the data type. So this chart here shows the performance gain for floating point operation from 32-byte vector to 64-byte vector. And the performance gain is up to 30% without alignment and goes up to 70% with alignment. And here we show the performance of integer, arithmetic, and logical operations. Here the performance gain is up to 40% without alignment and 80% with alignment. So the auto-vectorization not only benefits the classic Java code, but it also helps streams that was introduced in JDK 8. So here there is a lambda, which is a somewhat more complex expression than the previous example. And this lambda gets auto-vectorized. And if you would have used parallel along with this, this lambda, then you would see a gain across multi-core, and as well as you'll benefit from the vector unit on the processor. So here, this run is done on a single core, and you see there's a gain up to 60% with alignment and 64-byte vector. So as I mentioned before, JDK 9 has vectorization enhancements over JDK 8. So in JDK 8, given a simple loop like I showed in the previous example, there is a pre-loop, main loop, and the post-loop generated. The pre-loop does the destination alignment, and the main loop is the one that gets auto-vectorized, and the scalar post-loop is for tail processing. So in JDK 9, we now super unroll the vector main loop. Since the vector main loop is super unrolled, there is a vector single iteration post-loop which can do as much operation, remaining operation, using vector instructions as possible. So here is an example of reduction. So the highlighted portion of the code is doing the sum reduction of multiplication of array elements. And prior to JDK 9, reduction was not supported. Basically, if there was such a reduction in a classic Java code, the loop won't get vectorized, and you won't see benefit from vectorization. In JDK 9, the reduction is supported, and you can see that up to 2x gain is seen for this particular code. Here I show the vector post loop generated code, and you can see that the multiplication VP mul LD, that is a vector instruction, and the rest of the code is for the summation, the reduction operation. And summation is used extensively, for example, in convolution for image processing or k-means algorithm, matrix multiplication. So those all can get now auto-vectorized. We also recognized additional expressions in the vector loop and basically vectorize the loop. For example, the math.square root, if there is a square root performed on every element of the array, that now gets recognized, and we generate a vector square root instruction, the v square root pv. And you can see going from JDK 8 to JDK 9, we see about greater than 5x performance for this loop. So in JDK 9, there's another feature introduced called compact strings. So for this, we collaborated with Oracle, Charlie Hunt, Ziming Shen, Tobias Hartman, and many others. So basically, what compact string does is it tries to use 1 byte storage for characters of a string. In Java, by default, it supports the Unicode characters. That is, there are 2 bytes per character. But ASCII and English, the upper byte is always 0, so you can use a single byte per character. So without changing what's visible to the user, internally, the internal storage is changed from character array to a byte array. And if all the elements of the string fit within a byte, then the string elements are stored in a single bytes. And if not, the string is inflated and 2 bytes are used per element. So what this does is strings are extensively used in any of the Java programs, so it reduces the underlying storage that is used by the program. And not only that, most of the string operations are done at the back using vector instructions. So now, because the string elements are half the size, you can do double the operations behind. So there is a performance improvement is also possible. There is some overhead to check each element and inflate the string if possible. So both this, the memory size, which improves the garbage collection performance, and the ability to do double the operation gives benefit to the applications. So here, this is an example We had run SpecJBB 2005. This run was done on a Haswell desktop, and this is a peak run. So we saw about 5% performance improvement in the peak throughput for SpecJBB 2005. And this is a heap dump. So you can see that the total number of object instances is about similar between JDK 8 and JDK 9. The number of bytes that is used is reduced by 20%. And if you see the highlighted portion, which is showing the number of instances of character array and the number of instances of byte array. So whatever was character array before is now byte array with JDK 9. So in JDK 9, we also worked on optimizing the math libraries. Some of the key trigonometric and transcendental methods like the sine, cos, tan, exponent, pow, and log, they were optimized. And you can see gain up to 5x for these math libraries. These math libraries are extensively used in big data machine learning, the financial option pricing algorithms, and HPC. And here we show 3 micros for financial option pricing, the Monte Carlo, Box-Muller, and Black-Scholes. And they see gain up to 5x. For example, these algorithms use cos, sine, log, square root, pow, exp, etc. So that's why the gain. JDK 9, we also worked on optimizing the key crypto algorithms to benefit from the Intel architecture instructions. So Intel architecture provides AES-NI, carry-less multiply, and AVX2. Also, you could do 64-bit multiplies and get 128-bit results. So all that used at the back in the optimized stubs benefits the crypto. Java provides all the crypto through a provider framework, the Java cryptography architecture, and SunJC is the default provider. So we have optimized the SunJC provider methods through optimized stubs. And you can see up to 10x gain for AES counter and AES GCM decode. So the SHA optimization here is through the AVX instructions, the AES counter, and the AES GCM. His accelerations are through AES-NI. GCM also has a Ghash component that benefits from the carry-less multiply. And the crypto RSA is through 64-bit multiply, giving a 128-bit result, and the ADCX, ADOX instructions. So JDK 9, for compression acceleration, JDK 9 also added a feature. Prior to JDK 9, in JDK 8, the zlib was bundled along as part of the libzip.so. So now in JDK 9, uses the system zlib instead of the bundled zlib. So that gives a capability to the user to replace the system zlib with a software accelerated one or a hardware accelerated one. And here I have given 2 links. The software acceleration can be done either through the Intel performance primitives, or there is a GitHub project, which is listed in the document here, that could be used. And for hardware acceleration, Intel introduced Quick Assist as part of the Skylake, the chipset, Lewisburg chipset. So the Quick Assist also has compression acceleration capability through a driver and the library support that can be found at the link given here. So this one shows the performance improvement through software acceleration. I used the open source zlib from the link given here. And the performance shown is for the Calgary corpus data set, the compression portion. And the only thing I had to do was to get the source code, build the library, and set the LD library path to the built library. And we can see 1.5x to up to 3x gain in compression. So that was very encouraging. Stefan Freeberg added the CRC32C to Java 9. And Intel has an instruction called CRC32C, which can be used to implement the CRC32C of the Java 9 API. And this is basically the iSCSI CRC polynomial. And prior to JDK 9, and in JDK 8 as well as JDK 9, both have the Java util zip CRC32, which is a different CRC polynomial. And that was the Java util zip CRC32 is optimized using the carryless multiply. So the CRC32C, the new API, gives an additional 2x performance improvement over a previously optimized version. So, and we know that the checksum is extensively used wherever there is a lot of data. For example, Cassandra, HBase, they all use the checksum API. In JDK 9, lexicographic array comparison was introduced by Paul Sendoz. And we work closely with Paul Sendoz to optimize the array compare using the SIMD instructions at the back. And the array compare is used in Cassandra and HBase for key comparison. So, for example, Cassandra uses blocks of size 8K or 64K. So, and there is a checksum calculated for each block. So this is going to benefit that. And we have the underlying algorithm optimized using the SIMD instructions. And last but not the least, there was an FMA API added by Joe Darcy, which does the multiplication and addition, and the after addition, the truncation part is done after addition. So JavaSpec does not allow us to, optimize if there is a multiplication and addition. We can't optimize that using FMA because it expects us to do the rounding or the truncation part after each operation. So with this new API, now we can optimize FMA using the underlying architecture's FMA instruction. And FMA is used in convolution for image processing. It is used in matrix multiplication, in BLAS algorithms. So this is beneficial for HPC and machine learning. So I think both of us have shown a lot of new features that are available in JDK 9. So please download it, try it out, and give us feedback. And this is the legal disclaimer and optimization notice from Intel.